So today's notes, we're going to be looking at two proportions. So again, there are two samples. This time, though, we are not comparing the means. We are comparing the proportions. We are not going to fill out any of this, but what I do need you to write down, and this is really, really important, is there is no matched pairs for proportion. Matched pairs only applies to mean. So as soon as you know that it's a proportion problem, it's going to be the same every single time. You will not do matched pairs for proportion. We are going to skip around in the packet so that we can do the hypothesis test together. So you are looking for this problem, which I believe is on page 11, or at least that's what it says on my packet. Okay, so are teenagers going deaf? In a study of 3,000 randomly selected teenagers in 1994, 18% showed some hearing loss. In a similar study of 1,800 teenagers in 2006, 19.5% showed some hearing loss. Before we even do a procedure, I want to talk about part A. Between the two studies, Apple introduced the iPod. If the results of the test are statistically significant, when it says statistically significant, it means if we end up rejecting the null, can we blame iPods for the increased hearing loss in teenagers? No, why not? What's the stats reasoning? Right, this is not an experiment. So, not an experiment. If you were answering this on the AP test, you would have to use context. So you would say something like, this is not an experiment. The iPod is not randomized or randomly assigned to the teenagers. Now, why is it that an experiment does not show cause and effect? Or, sorry, backtrack. Why is it that an observational study does not show cause and effect? What are we more concerned about in an observational study, but less concerned about in an experiment? There's a vocab word I'm looking for. Bias. Okay, bias. Yeah, it's related to that. Confounding variables. Yeah, so if we could just remember that or write that down. Observational studies do not control confounding variables. And if we remember, confounding variables are just variables that are related to the response variable that could be messing up our results. So in the case of an experiment, we randomize the treatments. That is one way that we try to control confounding variables. Okay. So, part B is the new stuff. Do the data give convincing evidence that the proportion of all teens with hearing loss has increased? So when you read this question, we should see the word proportion. We know it's proportion. The other thing that should be going off in our head is we're comparing 1994 to 2006. So that tells us that we have two samples. So starting with our choose step. We are going to define our two parameters. Because we have two samples, we're going to need P1 for the first proportion and P2 for the second one. Just so you know, you do not have to use 1 and 2. You can use letters instead if that makes sense, like P of X and P of G. And if there's a context, normally we'll do that. It doesn't really make sense with 1991 and 2006. So I'm going to say P1 is the true proportion of all teens with hearing loss in 1994. And P2 then is the true proportion of all teens with hearing loss in 2006. This is a hypothesis test, so we're going to need our null and our alternative. We are going to assume that there is no difference. So our null is going to be that P1 is equal to P2. And then if you remember, that could be written as P1 subtract P2 equals 0. So those have the same meaning. You don't need to write both, but they have the same meaning. And then we're testing, is there evidence that the proportion of teens with hearing loss has increased, meaning the proportion is higher in 2006. So our alternative is we're looking for evidence that P1 is less than P2. Right? So 2006, the proportion is higher than in 1994. You also could see that written as P1 subtract P2 is less than 0, either one. And then we have to list off all the normal stuff. So this is a lower-tailed, or one-tailed is fine, 2-sample hypothesis test for proportion using Z. And we were not given an alpha, so I'm going to choose alpha to be 0.05. Remember, with proportion, you're using Z. Z does not have degrees of freedom. So we should not be listing degrees of freedom. Okay, for our check step. First assumption to remember is random. And this is what we talked about last class, that random is going to depend on the type of study that was done. If it's an experiment, the treatments need to be randomized. That's not the case here. This is an observational study, so our samples need to be random and independently chosen. So it tells us in the question, randomly selected, similar studies, so we're going to assume random again. The independence is not going to be stated, but we just need to ask ourselves, is there reason to believe these 3,000 teenagers in 1994 had any effect on the 1,800 teenagers in 2006? Probably not. So we are going to say the samples are random and independent, and that is stated. We talked about this last time, but I'm just going to remind us, it has to be plural. So it has to be clear that you checked this for both samples, not just one. Second assumption is the one that it always is, approximately normal sampling distributions. Again, that has to be plural. And we have to check for both. So we're going to check in 1994, and then we're going to check in 2006. Okay, here's where I'm going to ask us to dig deep a little bit. We're going to write ourselves a note off to the right side. Okay, so our note has to do with one sample proportion. So this is what you guys had a test on recently. So when we had one sample for proportion and we were checking the approximately normal sampling distribution, do you remember that it was slightly different when you did a confidence interval versus a hypothesis test? It was still the NP idea, but what was the difference in a confidence interval versus a hypothesis test? Augie? Okay. In a confidence interval, in a hypothesis test, we used P. And if you remember, that came from the null. In a confidence interval, though, we didn't have P, so we had to use P hat instead. And that came from the sample. Okay, so if I'm thinking, two samples, gonna work almost exactly the same, right? I would think to myself, well, it's a hypothesis test, so we're gonna use P from the null. Does that work though? Right, if we're checking for both 1994 and 2006, do we have a value for P for both of those? No. So we don't have a P to use, we're gonna have to use the sample numbers. Because of that difference, I would highly suggest you don't use any notation. Just jump right into the numbers. So if we look at 1994, we have 3,000 students and 18% of them had some type of hearing loss. So when we multiply, that's 540, which is greater than or equal to 10. And then we have our 3,001 subtract 0.18. And that ends up being 2460, which is definitely greater than or equal to 10. Okay, and then in 2006, I don't know how many people there were, 2006, 1,800. And 19.5% showed hearing loss, so that's 351. And then we have our 1,801 subtract 0.195, and that gives us 1,449. I'm just going to put a check mark because that's true. Again, it needs to be very clear that you checked this for two different distributions. So I would say what I do to show that this is plural is I actually write out the word distributions, and then I put these two labels here, and that helps to kind of cover my bases. Okay, do we need to check the 10% rule? Did we do sampling? Yes, we sampled teenagers. Is this a finite population? Is there a set number of teenagers? Yeah, and probably sampled without replacement, so we do need to check the 10% rule. Okay, so the 3,000 needs to be less than 10% of the first population size. So that is big N and a 1. So our big N, 1, has to be greater than 30,000. And then our 1,800 has to be less than 10% of our second population, big N2, which means big N2 has to be greater than 18,000. And we need to write a sentence. This is where people tend to go wrong, is when we write the sentence for proportion. A lot of people want to say, there are more than 30,000 teenagers with hearing loss. That's not the population, though. So we have to ask ourselves, how was this data collected? We had a bunch of teenagers, and then we just measured, do you have hearing loss, yes or no? So the population is just teenagers. And then we looked at the proportion with hearing loss. So I'm going to say, yes, there are more than 30,000 teens in 1994 and more than 18,000 teens in 2006. Again, I know I sound like a broken record. You have to make sure that you are showing evidence that you checked this for both. Okay. The calculate step. I'm going to be very clear with you right now. I'm going to show you the formula. The formula is kind of crazy. I'm showing it to you just so that you see it, and then we are going to do everything on the calculator. Actually, we're going to do the calculator first. Yeah, we're just going to do the calculator first. So, where do you think you go? Okay, you're going to go to stat. you're going to go to tests. And we've talked about the one for proportion says proportion. So I think it's 7 or 8. You're looking for 2 prop Z test. Find that? Okay. So then it's going to ask for x1, n1, x2, n2, and the confidence level. Nope, not confidence level. It's going to ask us for the direction. All of this looks so good so far? Okay, your x is the number of successes, which in this case, we are not given, we're going to have to calculate. So the number of successes is the number of teens with hearing loss in 1994. So for x, you're just going to put 3,000 multiplied by 18%. And then your first sample size is 3,000. Likewise, for our second sample, out of the 1,800 teenagers, 0.195 showed hearing loss, sample size of 1,800. And then if we remember all the way from our alternative, this is a lower-tailed test. So if you do all of that and you hit calculate, I believe you get a z-value of negative 1.29. And then the number very below that should be the p-value, which is about 0.098. Did you guys get that? Okay, I want to remind you, x has to be a whole number. So in our case, we did 3,000 times 0.18, and that gave us a whole number. If it gives you a decimal, the calculator won't calculate it, in which case just round to the nearest whole number. Okay, we good so far? I'm going to show you the formula, just so that you see it and so that you know where these numbers come from. But you don't need to show this. Okay, so it starts with z equals. The numerator is not too bad. When we did mean, we took our sample means. Well, in this case, we're taking our sample proportions. So P1 hat subtract P2 hat, subtracting P1 subtract P2. And this P1 subtract 2 just comes from the null, which 99.9% of the time is just 0. And then if you remember, in the denominator, when we did mean, it was a combination. If you remember, we added the variances and we took the square root. Similar idea. So the standard deviation for this P1 hat, if you remember, would be the square root of P1 hat, 1 minus P1 hat, all over N1. Sound familiar? Okay. Similar idea, but a little bit different. The square root, instead of P1 hat, we use PC hat, 1 minus PC hat over N1. And then we have PC hat, 1 minus PC hat over N2. And right now you should be thinking to yourself, what the heck is PC hat? Never seen that before. Which you haven't. There is another formula where you would have to find PC hat first before you can plug it in. PC hat is N1 P1 hat, add N2 P2 hat, over N1 add N2. This is a pooled value. I hope we can see that this would be a fairly complicated or time-consuming calculation, which is why I'm not having us do it. You do not need to know this formula. You do not need to show it. I'm showing it to you. If you are actually doing this hypothesis test, what I need you to show is I need you to show this, and then the test statistic and the p-value. That's all. So everything that I have below that or everything that's not highlighted does not need to be shown. All I want is what function you did in the calculator, what your test statistic was and what your p-value was. The AP test will accept that for full credit. You do not need to show what is in black. You do not need to show what you put in the calculator besides what you chose. We are going to, of course, draw a graph, though. All I want is that negative 1.29 with it labeled and shading the appropriate direction. Okay, ready for a conclusion? Okay, p-value 0.098, and that is greater than 0.05, so we will fail to reject. So I fail to reject the null. As there is not convincing evidence As a reminder, our alternative was that P1 was less than P2. So I need to word this evidence in terms of proportions. So I fail to reject the null as there is not convincing evidence that the true proportion of teens in 1994 with hearing loss is less than the true proportion of teens in 2006 with hearing loss. So I'm just saying I failed to reject the null. There's not enough evidence for the alternative. At this point, I would want us to look at the question and ask, did we directly answer the question? So the question says, is there convincing evidence the proportion of teens with hearing loss has increased? So I would say we did not use those exact words. So I would then answer the question using the exact words from the question. So no, there is not convincing evidence that the proportion of all teens with hearing loss has increased. And then we are, just for fun, going to interpret our p-value. Okay, assuming, normally we write the null is true. I want to write that in context though. So assuming the proportion of teens with hearing loss is the same in 1994 as 2006. So assuming P1 equals P2. So all I'm saying is assuming the null is true. I've just done it in context. 0.098 is the probability of a difference in sample proportions of it's negative 0.015. How I did that is I took that 18% and I subtracted the 19.5%. So I took our two actual proportions and I subtracted them. The probability of this difference or smaller, since it's lower-tailed, by chance alone. Okay. Questions for me? Okay. Oh, I forgot to show this to you. This is the formula sheet. So I just want it, like we've looked at it quite a few times, but we are looking at the two proportions today. And so you could theoretically figure out the standard deviation for the hypothesis test formula. Here it is with PC. I've never seen you be asked for it, but it's there, it hit you. Okay, this is the problem that you are doing. You are doing both parts A and B. There is nothing I need to tell you. You should be able to do the entire confidence interval. You will be doing this on your desks. I would like you to just use your calculator to figure out the interval. So you should be able to do that and then interpret. I also want you to do part B. Questions, comments? Here is my answer. The thing that I wanted to make sure we were cognizant of is that this is an experiment and not an observational study. So we needed to check that the treatments were randomly assigned, not the random and independent samples. Independent is not in this at all. We needed to make sure we said that it was a Z confidence interval, 2 sample. I think all of that was fine. You didn't have to do the 10% rule because there were volunteers. And then formula-wise, I don't expect you to show this, but I expect that we could figure it out. What I want you to notice is the formula does not have PC in it. PC is only for hypothesis tests. So you just subtract your proportions, plus or minus Z, and then the standard error you can find on the formula sheet. And then the conclusion, you've already written a few times. Part B, I'm looking for, yes, there's evidence, because 0 is not in the interval. Did we then explain what 0 meant? 0 would indicate that the treatments are not, 0 would indicate that the treatments are equally effective. So I have an extra word in there, that the treatments are equally effective, but it's not a plausible value. And then do you remember how I said last class that once or twice I've seen the AP test require you to write this last sentence saying what would happen in a hypothesis test? If you remember, write it. It's probably a good idea. It's not a requirement, though. So if we were to do a 2-tailed hypothesis test instead, where alpha is 0.05, we would reject the null. And then the last thing to say, I didn't put this, but is there convincing evidence? Hopefully you guys used that word convincing, because I've also seen that College Board is pretty picky with having that word there. How do we feel about this? Besides the fact that it's long. Okay.